And I will share my screen. Let it come up, move my stuff around here a little bit, get you guys ready to go. Maybe slide this over here if I can. Okay, just to check, you guys can see my PowerPoint, you can hear me, are we ready to go? All right, get some yeses here. Okay, we are doing number systems. So you did a lot of homework on this. I'd only seen a few in there. We're grading them kind of for completeness. It looked like you were getting the gist of the number system. So this lecture, we're going to go over the number systems, and it'll go fast. I can slow down and do any problems that you want, or give you some examples, or have an office hour with you if you don't understand the math. But usually this, the math part for the quiz and everything goes pretty well, usually for everybody. So once again, I take attendance, everybody. I got a few labs out. I don't know if I got most of the labs in, actually. I think everybody might have been caught up on what the labs that they owe me or not. If not, let's figure that out. But I'm pretty much caught up, I think. All right, panel view. Lab for still needs graded. Yeah, did you turn it in? Oh, okay, get them turned in. I've turned them back. I've graded them, and they should have came back. So, let's just be sure we got them and that they got graded and that they got there. Okay. Unless you well, look, I'll look. Maybe I've got them in my folder. All right, panel view. I say very few problems with that lab because it was just kind of work your way through it and tag it out and just build it step by step by step, just to show you some functionality of the HMI, the panel view. And it's very similar to that last Siemens one you did in the last class, where you can enter timer values and counter values. And this one just had some indicators and stuff that you could throw on there to show that. So if you just follow the instructions, it went pretty well. The same old issues are present, and I think you're getting better at them. And this is right here. What do you need to make sure the communication path gets set in the panel view plus at runtime? So you want to, when you want to be sure you are online, you want to launch FactoryTalk View, and you want to run RS6 Enterprise Communications, you probably have to create the shortcut. If there's a shortcut that's not working, I went in there and I deleted old Ethernet paths if you had one. Delete the old ones, just broom out of there, add the new one, and then drill down, select your CPU. It should say your lab name on it, right? And remember, it scrolls across the CPU right here, whatever your name is. And so when you be sure that you are picking your lab, you're online, a copy to runtime. You got a copy design to runtime. Apply. You got to hit apply, click copy runtime, click OK, and then it should be there. You might have to go back and run that again, even after you built that up. But if you go through this, it seems to come through. This procedure, scale of 1 to 10, you getting good at it? Where are we at on this? The scale of 1 to 10 to set up the RS-Links Enterprise Communications. Got an 8 to 9, 9. All right. Well, it's to get this practice, and you want to just be sure that you run it over and over. It's a big pain in the butt. You know, that Siemens just did it all for you, which was nice with a single piece of software. If you're in the browser tag window and you can't see the tag you're looking for, what step should you do? You should go online, and then you should go and refresh your tags, and then it will pull your tags, and then you can go online and see all your tags. At that point, you can go offline if you want. That way, you've kind of brought the tags in, and you have offline tags, and then you can go ahead and build your program up from your HMI. Scale of 1 to 10. Everybody feeling good about this, about going online, rebrowsing, getting your tags, and being sure that they're all there? Yeah, you just want to be sure you're online with all this stuff. What is the process for programming and accessing the second screen? You want to create the second screen, add your items to the screen, then you got to save the screen, and then the name that it will ask for the name, and then you add the go to. Now remember, the main you can't get rid of. It's like the main OB in Siemens. You have to program on. You're going to program on the main. If you program and call something else, it's not what's going to launch. The main is what's going to launch. you know, and then you would have to have a go-to or something like that. Okay, so program the main and then program your other screens that are your go-to to the other screens. All right, and this lab has some other screens. So somewhere on your main is where you're going to call the other screens. Feel good about this scale of 1 to 10 about saving it and then having access to more screens and that you can do go-tos and jump between the screens and all this kind of stuff. Okay. There's a quiz on the HMI tonight. It's hopefully pretty basic. All right, moving on. Bad scheduling. I got a little example here. You can watch this video if you want. But as many of you know, I tell you I resell Allen Bradley equipment. And some of the things I resell is processors. I love getting processors, and then I love sometimes uploading them and see what they are. Here's one that I had uploaded that I did want to share with everybody. And here's what you get to with bad scheduling on a Slick 500. Okay, and so right here, what you've got is you've got your jump to subroutine here. And then you've got all these bits and all these eyes. I got an SDN here. So there's some device net or something going on here. If I click my IO configuration, I got a device net scanner module. I was showing you some of this stuff before. Once you get that device net scanner module, your data, the volume of data that you could be looking at to try and find something gets crazy. But here's bits, here's IO, there's another jump to subroutine. Unconditionally scheduled subroutines. That's what I'm telling you. You're going to see most of the time. But there's no run comments. No nothing. There's nothing on here. And when I start going into my subroutines, sorry, ladder 50 here. Here's where, oh my gosh, I got a subroutine within a subroutine. So this subroutine is calling a subroutine within a subroutine. There's all kinds of bits. There's no labels. Here's another subroutine right here, 51. Calling you 80, ladder 80, a subroutine within a subroutine. Look at all this interlocking and stuff they got. Oh, it's jumping to a subroutine here. So this 80 is this 80 is calling 84 right here. 80 is calling 84, which was called out of 52, which was called out of 2. Does that make sense? A subroutine within a subroutine within a subroutine within a subroutine. Holy moly. How are you gonna figure out what is going on here? So I love downloading this stuff and trying to figure out, you know, what is going on, but I call this bad scheduling. You can have all this stuff, definitely. Yep. So, you know, when I downloaded this, go online and everything with it, you know, a lot of times there's nothing there, you know, so I'm like, man, what is going on? Here's something. Here's one, IO slot enabled. That's nice. Great. It was nice, you know, that's a system bit right there, you know, but why not, you know, put some of this other stuff in here or come up with a name or something like that. So bad scheduling, just do the best you can to document stuff. You'll make somebody happy. All right, chapter 3 is the number systems codes, which you guys were working through, and we're going to jam through this. Like I said, it's not very much. If you want to stick around at the lecture or ask me some questions or don't understand this, that's what I'm here for. I will show you some stuff about the rates and stuff on the software here as we go. Decimal system. We don't need to get into the decimal system too much because that's what you grew up on. Other than to point out a couple things. Number one, the numbers are 0 through 9. 10 is not a number. 10 is a number, but it's made up of 2 numbers that were from 0 to 9. Okay, and so when we do this and we look at the decimal, remember, this is the ones, this is the tens, this is the hundreds, this is the thousands. You just multiply by 10, 10,000s, 100,000s, millions. You understand this, you feel good about this. And when you come up with a number here, it is going to have a 10 right here, 1962 base 10. But we don't put base 10 on it because you use decimal numbered systems in your life, and it's just assumed that everything you learned through school up to now was base 10. So you're not necessarily going to see the base 10 there, but you could get in trouble with a PLC. Binary system. We've talked a little bit about this. This is on or off, high or low, true or false. You know, ones and zeros, high, you know, whatever, true, false. How many times you can say it? That's what we've done a lot on with the binary system. When you can, in the computer or the PLC loves the binary system. We've been looking at words and double words, we're thinking about ints or dints quite a bit, or the register. The register would be the 16-bit word. If you hear this terminology, the register, it reads least significant bit to the most significant bit. And so therefore the first one here is the ones, the twos, the fours, the eights, the 16s. If you had another one, the 32, the 64s, etc. And it just reads least to right. So we have 1 1, 0 2s, we have a 4, we have an 8, we have a 16, and you add them all, you multiply and you add them together, you get a 29. Okay. When you look at these tables, these were all in the textbook about, you know, your decimal, your octal, your binary, and notice that binary only counts with 2 numbers because there's only 2, 0 and 1. 0 and 1, and then what do you have to do? You have to start over with a 0 and put a 1 on it. Just like when we got to 9, we had to put a 0 on it and start with a 1 0, a 10. And so same thing when we on the decimal, when you get to 99 and you run out of numbers, you got to go 99, you got to go 0 0 and put a 1 in front of it, 100. So that's all this is doing. When you run 1 1, when you run out of numbers, you got to put a 0 0 and put a 1 in front of it. And so 101, 101. This is just how the binary counts up with 2 numbers. So as you look at the binary count up here, and the way I explained it with a 0 to 9 instead of 0 to 1, scale of 1 to 10, you feeling good about the way that binary counts? This right here. Everybody feeling good about this right here? I could break it all down. I could do is a 3, a 0 1 2 3. If you only had 3 or 4, 0 1 2 3, then you'd have to go 0. So 1 0. So 0 1 2 3 1 0, like that. So yeah, okay. I think we're good on it. Wonderful. Conversion problem 1. It says 1 1 1 1 1 1 0 to decimal. So that's what I was just showing you. This right here is the 1s. This is the 2s. This is the 4s. This is the 8s. This is the 16, and this is the 32. So it looks like I have a 32. It looks like I have an 8. It looks like I have a 4, and it looks like I have a 2. So 32 plus 8 plus 4 plus 2 is what I'm seeing. 10, 44. I got 46 on that, unless I'm moving too fast. 46 on that. Let's see what this, do I have it right here? Where'd it go? Is that what you guys came up with, 46? Where'd it go? Good on that? Everybody, is that right? Is that what you guys got, 46 on that? Looks right. Everybody feel, scale of 1 to 10. Can you do the binary? If I give you a binary, can you convert it to a decimal? The problem is if I gave you a 32-bit word, you'd be a 32-bit word. You'd be doing 64s, 128s, 256s, 512s, 1024s. You'd be up there to, you know, a billion something on the last one, right? It'd be rough, or almost a billion. Okay, I feel most people do well with that first one there. All right, what do I got here? PLC memory is organized using bytes, single words, or double words. We said the byte was 8 bits. A single word, or often referred to as the register, would be 16 bits, and the double word would be the 32 bits. Okay, and we just, it starts least significant to most significant, works this way. These are the 1s, the 2s, the 4s, the 8s, 16, like that. Works your way across there. Okay, and then when you get a bunch of them here, it's called a file. If you get, you know, word, the first word would be 0000, and it might have a bunch of 1s and 0s in here. The next word, 0001, might have a bunch of 1s and 0s, and this one, 1s and 0s. When you get a bunch of words together, it's called a file, and that will be what we'll start working on next. Bit transfer and file transfer. Okay, but that's the way that these are organized. We talk once again about register. So each digit is a bit. A byte is 8. There's 8 of these right here. A word is 2 locations. You put 2 of these together. A double word would be 32 bits. You know, now we got operating systems that are operating on 64 bits. Windows, you know, 10, Windows 11. These are 64-bit processors. So they're big words. The most significant represents the largest value. In this case, it's the 6. The least significant would be the one over here would be the 7. So those are at least in most significant bits. decimal to binary, okay? This is the way that I do it. If you have a decimal and you need it to make it a binary, divide it by 2, which is 28, remainder 1, because 28 plus 28 is 56. Remainder 1 is going to be 57. 14, or half of that's 14, remainder 2. Half of that's 7, remainder 0. Half of that is 3, remainder 1, because 3 plus 3 is 6, plus 1. Half of 3 is 1, remainder 1, so I got 1, 1, 1, 1, 0, 1, 1. When you do this, and when you do this on the quiz or whenever you're doing it, you got 57. I always check it. So this is 1, 2, 4, 8, 16, 32. 32 plus 16 plus 8 plus 1 is 57. I always check the math, all right? Conversion problem 2, 47 to binary. And I could write it up on the sheet, but it's right here. Yeah, I'll write it up on the sheet if you want me to do it on the sheet. 47 divided by 2 is going to be 28, remainder 1, right? No, that'd be 56. It's going to be 23, remainder 1. Half of 23 is going to be 11 with the remainder 1. Half of 11 is going to be a 5 with the remainder 1. Half of 5 is going to be a 2 with the remainder 1. Half of 2 is going to be 1 with the remainder 0. So then you work your way back up this way, all right? So it would be, let me see, 1, 2, 4, 8, 16, 32. Let's see. So if I go 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1. Let's see if I did this right. 1, 2, 4, 8, 16, 32. 32 plus 8 is 40, 44, 45, 46, 47. That's how I got it. And so whatever answer I got, I just check it. Just do the 1, 2, 4, 8, 16, 32s and add them together and see if it checks it. Now, when you get really good at this, you can, and you don't want to work the math out, you know that you're going to start with the biggest number here of 1, 2, 4, 8, 16, 32, 64, 128, whatever that fits into it. And so the biggest one, 64 doesn't fit into it, 32 fits into it, okay? So then you can just go, right, hey, I need a 32, right? Now, do I need a 16? Well, 32 plus 16 is 48. So that doesn't work. It's too big. So therefore, I know that I need an 8. So then I got 40. Can I add a 4 to that? I can. 44. Can I add a 2 to it? A 46. Yes. Add a 1 to it. A 47. You can work it up that way if you see it in your mind like that, to just start adding to get what you want. And then this was the way that we did it, dividing by 2. So converting a decimal number into binary, scale of 1 to 10. How are we at on that? 10. What do we got here? 9. 10. Remember, you can always check it when you get done. Like pick 13. I'll do 13 for you. You want to do it? You want to do it the easy way or the hard way? 13. Okay. So I got 1, 2, 4, 8, 16. I can't have a 16 because it's too big. So at my 8s, I'm going to have a 1 right there. So I'm going to have a 1, okay? And so I got to fill up 5 more. How about at my 4s? I'll put a 1 right there at the 4. So that's 12. 2. Well, 12 plus 2 is 14. It's too big. And then a 1, I'll take a 1. So 8 plus 4 plus 1 is 13. Maybe you work it out that way. Maybe you take this and divide it by 2 and do 6, remainder 1. Divide this in half and you get 3, remainder 0. Divide this in half, you get 1, remainder 1, and you write it out. 1101. 1101. But you just check it when you get done to see if it adds up. And if it doesn't, you can say, oh, I need a 1 right here. I need a 1 right here. So hopefully you can get the number to be what you want, okay? Negative numbers. Well, I know it does that sometimes. You know what I mean? It gets tired of sharing, and then it drops out. I reset it. Can you guys see me and hear me again where it says negative numbers? All right. So negative numbers. You can do negative numbers because, you know, we have counters that go up and counters that go down. This is binaries cannot use positive and negative symbols to represent the polarity of a number. So in assigned binary numbers, the leftmost bit is equivalent of a plus or minus sign. So what you're doing is you're taking your 16-bit register and you're counting from right to left. The leftmost bit becomes representing the plus or the minus, a 0 or a 1 to be the plus or the minus, okay? Which means that you lose the biggest number that you could have there, because the one all the way on the left, when you put a 1 in there, that's the biggest number that you got. It's not the 1, the 2, the 4, the 8, the 16, the 32, the 64. It's whatever, it's the 16,000 or the 32,000 something over there, right? So if you get rid of that 1, you lose the biggest number, but at that point you can do plus or minus with a sign bit, okay? Where 1 indicates a negative and 0 indicates a positive. Hexadecimal systems. So in a hexadecimal system, they count 0 to 16, but you're like, wait a minute, there's only 10 numbers, 0 to 9. Well, they go 0 to 9, and then they start using letters A, B, C, D, E, F, and then they would start over again right here, right? This would become 1, 0, 1, 2, 1, 3, 1, 4, all the way up to 1A, 1B, 1C, 1D, 1F. So it would use a hexadecimal numbering system, and it's showing you the equivalent ones over here. When these ones run out of numbers, they go 0 and then 0, 0, and they got to put a 1 in front of it. And when the decimals run out of numbers, they go 9 and they got to go 0 and put a 1 on it, all the way up to 99, put a 0, 0, 1. This would do the same. You got to put a 0 here and put a 1 on it and then start going again. So hex is a base 16 system. What's this? Conversion activity 3. What's that showing? Conversion 1B7. Okay, so here's my 1B7. This is the least significant. It's the 1s. This right here is the 16s. This one right here is the 16 times the 16s, which is the 256s. This one here would be the 4,096s, if that's what you had. The 16, or more than that probably. Was it 4,000? Yeah, 4,096s. You know, times 16. It just keeps getting the power of it. So 1B7, we got 7 1s. You got B. What's that? What is B? Well, if you go back to here, you can see that B, remember we run out of numbers here, B is 11, represents 11, okay? So we got 11 16s, and we got 1 256. Add them all up, okay? And then that's our base number 10. So hexadecimal counts to 16. That's a little bit different because we're starting to use the letters. Scale of 1 to 10, hexadecimal seems to make sense to you. I don't see it a lot, but it's there. Okay. Yeah, it makes some sense. Take a look at the stuff in the book. It kind of just lays it out, you know, why you would want to use, you know, hexadecimal. But it's just, remember, these number systems are just how many ever numbers that you're working with. So, you know, I don't know what to say it, that, you know, this is 0 to F is what it counts. And then you start over again. 1 0, 1 1, 1 2, 1 3, 1 4, 1A, 1B, 1C, 1C, all the way up to 1F. And then you go 0, and then you got 2 0, 2 1, 2 2, 2 2, 2A, 2B, 2B, up to F. And you keep going all the way up to whatever FF. And then and at FF, it becomes 1 0 0 again. And you just keep counting from there, okay? Just like we would do with our decimal, okay? Binary coded decimal. That's another one that we got into a little bit this week. My BCD. Binary coded decimal uses 4 bits to represent each decimal. In binary coded decimal, you will see a little bit. So once again, here's our decimal, here's our binary. Our binary coded decimal is going to use 4 bits in binary form to represent the first number, okay? And so if we look at this as binary, 0 0 0 0 is 0, and this is binary 0 0 0 1 is 1, and it would be 0 0 0 1 0. It's got the extra zeros on it, okay? And so if you were to convert binary to decimal, that's what everybody said they're feeling pretty good about, converting binary to decimal. Well, what this binary coded decimal does is it allows you in your first group here to come up to 1001, which is decimal 9, okay? And then, like we said, with everything, when we get to the end of these numbers, we start over with zeros, and then we put a 1 here, okay? And so when you get up to 10001, your number would be 99, okay? And we got some examples here. 1678. So the 1 is 0001 in binary because there's a 1 right there. How about the 6? No 1s. I got a 2 and I got a 4. 4 plus 2 is 6. That's what it is. My 7 is 1 plus 2 plus 4. 1 plus 2 plus 4 is 7. And my 8 is 1, 2, 4. I've got 1, 8. So just put them all together. 0001 is the 1. 01110. 01111 is 7. And so that becomes my binary coded decimal, where this is the 1, this is the 6, this is the 7, and this is the 8. And that's what we're using for the lab to take the thumb wheel in, because we have 16 inputs. And so I'm bringing in a number here from the thumb wheel, from the input module, and we're making it into, taking this binary coded decimal and turning it into a number. It is not binary, okay? Conversion problem 4, what's that? 768 to BCD. 7. It is 0, 1, 1, 1, 1, 1. That's a 1, a 2, and a 4. That's 7. 8 is just not a 1, not a 2, not a 4. There's my 8. 6 is 1. Here's a 2 and a 4. 2 plus 4 is 6. And this is 1 plus 2 is 3. So my decimal number 7863 becomes binary coded decimal 01111 right here. Scale of 1 to 10. How does the BCD look? It's usually a little bit simpler for people to see, you know, that the applications. Why would you want to do that? And that's kind of what the lab is showing here for the binary coded decimal. All right, very similar feel to the binary. Okay, to distinguish BCD numbering system from a designated place to the right of the units, a BCD. So if I see this number 011, 010011, this is not 1, 2, 4, 8. That's 9, 16, 32, 64. This is not 64 plus 9. This is not 73 right here. This is not 73 converting binary to decimal. It is 0100, which is there's the 1, the 2. That is 4. Okay. And this in 1001 is 9. This is 49, not the other number if it says BCD on it. Binary has the 2 on it. Okay. So it'd be a little bit different. Okay. What does this all mean? Well, we're using a thumb wheel switch as our input device. So those that have already started by the lab and looking at it a little bit, we talked about that in the past when you wanted to bring a word in, like I want to make 236 chocolate chip cookies, 236. How do you get 236, the number, into the PLC? Well, you could do this. If you wanted 236 chocolate chips on your machine, you could put a push button right here, and you could do a counter right here, and you could start pushing this button until it hit 236 on the accumulated value, and then hit enter, and bang, run with that number with the counter 1 accumulated value. All right, that's a big pain in the butt if you want 236 chocolate chip cookies. All right, so you know, back in the day when you wanted to bring in a number, or a proc sensor with a counter, yeah, but still you got to like hit that. What if you wanted like 35,000 widgets? You got to push that. You got to hit that proc 35,000 times. Or whatever, you know, it was a problem bringing in numbers. And so what you could do is that you would bring in the number using that thumb wheel, okay? And when you click that when you click the number right here, 1, 2, 3, 4, 5, 6, 7, 8, it is wired into the input module. this thumb wheel is, and it's wired into the 1, 2, 3, 4, the first 4 inputs. Okay, if you have a 2 display thumb wheel, okay, so if you have a thumb wheel right here where you can do 2, maybe you could put a 1 and a 3 here. Okay, this would go into 4 of the inputs, and then this would go into the next 4 inputs. Okay, wires in there. But what we have is our thumb wheel is got 4 displays, and it's binary coded decimal. And so 4, 4, 4, 4, these run into the 16 inputs. Okay, and so it's set up that when you have a 1 on here, and then you look at your card, you got 0, 0, 0, 1 on your input card, you would see that the 0, 1, 2, the third input would be on. And on this one right here, it'd be 0, 0, 1, 1. So that would be, these 2 input lights would be on your input module. And this one would be 0, 1, 1, 1. And this would be 0, 1, 1. 0, 0, 1, 1. So that is what would come in from the thumb wheel. If you set it to 1373, it reads this number in because these are the inputs that are on. Well, that looks like garbage. What are you going to do with how does 001001110, how does that equal 1373? Binary, it doesn't. We already said that this number is a BCD is not the same as if it says binary 2, because this is binary 2. It's a 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2000. We got a 4096 in there. So 4096 is way bigger than this. It's not a binary number. It's a BCD number. That is what is coming on into the PLC. Okay. And so when you click this, it's taking, that first one is your input, generating the BCD number. Okay. The thumb wheel operation, typically when you work with this stuff, if you had one that was just hardwired and soldered up with an integrated circuit, you would have a BCD to 7 segment decoder. And what that does is it takes, like I said, you can take these switches, this first switch, this is a 4-bit BCD input for the first number, and it would take that in, and it runs through this BCD, and it's going to generate the numbers here, like I was showing you. And then same thing on the output, it's going to generate something. We need to take that number 10101111, whatever it is, convert, knowing that it's binary coded decimal, and be sure that our display here can understand what this is. So if for some reason I get 0000000, this says turn on A. There's the top. This is turn on B, C, D, E, and F. So turn on A, turn on B, turn on C, turn on D, turn on E, and turn on F. Well, that's a big fat 0 right there. All right. So if I'm getting zeros out of my decoder, it's going to put a big fat 0. What if I wanted a 1? Here's my 1 right here. So that means turn on B and C. So B and C is on. Yep, there's a big fat 1 right there. Okay. So we are taking some of this hardwired BCD to 7 segment decoder, and we're using a PLC instruction to kind of do this. Okay. There's the addition here. We're not going to dig into addition. There used to be a lab where we did a lot of bitwise logic, division, subtractions, whatever. I don't think I got this on there, but you could do this if you wanted to. 1 plus 1 is 0, and carry the 1 because it's 2. 1 plus 1 is 2, right? And so 2 is 0, 1. So it'd be 0, put the 1 up here. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1, so it'd be 1, 0, 0, 0. And you can see that addition would work like this, but we're not doing addition, subtraction, everything like that. So we used to do that. It's a little bit overkill. You might get into it someday. Just wanted you to be aware that you can add, multiply, whatever binary numbers. Okay. So want to talk about the radix here real quick. And so I'm going to jump to the lab. And so what we've got going on with the lab right here is this. Okay. So this is the instruction that the lab shows you called FRD. And this is replicating that hardwired circuit. You could buy a BCD encoder circuit and wire it up and have it do these things, but the PLC is doing it for us. We are taking in the entire input module, local 4 data, I guess. That's where you have the wheel wired into 4, or local 5, slot 6, slot 7, whatever slot you're in. That's apparently this one is right here. And it's taking the BCD in, the 1001, it's taking that BCD in that I showed you right here, this BCD number from whatever our wheel was set, okay? And the purpose of that logic is to then create the number for it. And it would create the number 1373, because that's what it is. It's doing the math for us. Now, we are using that number 1373 if you were adding, subtracting, moving stuff around. One thing to note, and I'll say this 2 times, because I always say two times. A lot of times when you are working with a word or register a double word, you have to, whatever the instruction is, you have to put it in a destination. And then sometimes you have to move it to another temporary destination, because you can't just take this answer sometimes and then plug it into your program, plug it into your variable frequency driver, plug it into your output, or plug it into whatever. A lot of times you got to take this tag right here, and that's the manipulated data. You got to take the manipulated data, and then you got to move it to another tag. Now, at that point, storage 1 right here is fair game, man. Go to town on storage 1. But it won't sometimes let you go to town on storage first. So scale of 1 to 10, do you understand that sometimes you got to take your manipulated data and you got to move it to a different tag name? It's the same value. All right, I'm telling you right now. Yeah. Nicola, that's a 9. Okay, Nicholas is 9. Nice try, buddy. Okay, so just be aware that as we get moving forward, and I'll catch myself sometimes, oh yeah, do a move it into a temporary destination, storage 1, storage 2, storage 3, whatever you want to call it, Dorito 1, Dorito 2, Dorito 3, and then you can go and go to town on it. Okay, we are doing the calculator. We're doing move and adds and all this kind of stuff, and we could do bitwise adds and subtracts and multiply for this lab, but really the HMI isn't, or this is just taking that number and this right here, the computer's doing that, the add of the binary, but it's really, in your eye, anything you're going to see is you probably want to see it as decimal. You can look at a binary if you want, but it's going to be decimal. Okay, so here's some more examples on this. So what I got right here is I got something called parameters on my local tags right here. Okay, so I'm looking at my tags right here, and you can see that I've got my storage 1 right here, and it's a dent, right? And I can go to my monitor, my tags. When I'm looking at, my value here, I can see the radix. Here's the style. And a lot of times you're looking at decimals. So if you're adding storage 1 and you're adding storage 2, and storage 1 is 10 and storage 2 is 8, okay? Well, 10 plus 8 is 18. If you really wanted to see, what this looked like when it was added, you could come right here and you could look at 10 as a binary. There it is right there. 1, there's a 2 and an 8. A 2 and an 8 is 10. And here's the binary right here. There's an 8. And when you added these together, you would get 1 0 0 0 1 0. Because there's the add right here, and let's see what my add is doing. My add is moving it to answer. I could see answer right here as a double word if I wanted to, but you don't need to. But but you might want to someday. Okay, so where's answer at? So my answer right here is, if I go to my monitor tags again down here, I'm seeing it as binary. Really, you would want to see that as decimal. And so, you know, if this was working and I added those two numbers together, this would have been 18, okay? But you can go back between decimal and binary. And let's see just see what this did for this routine right here. I guess if I went down, did this and downloaded it, it would take this answer right here that's shown in a double word, and it would push it back to the radix of being a decimal, because you probably want to look at it as it's decimal. But a lot of times you want to know what the binary looks like, especially if you're taking a look at inputs and outputs. Okay, and so here's an example right here. It says, let's say you want to, I thought I had something. Let's say you wanted to turn on some lights. Let me see what I got. I'm going to jump ahead in this a little bit. I'm showing, oh, I want to turn on outputs 1, 4, 7, 10, and 12. All right. I want to turn on outputs 1, 4, 7, 10. Okay. So when I'm working with the math like this, I often have a tag called math tag. I'll make a tag called math tag. It doesn't serve any function except for me to cheat and do a binary or a hexadecimal conversion or whatever online quickly. So if I wanted to turn on these items, I wanted to look at this. Oh, where is this? Hang on. No, just cancel. I was right there before. No, go. So if I wanted to come right here on my math tag, and I wanted to look at this as binary, okay? And I said I wanted to turn on some outputs. So I don't know what I said my outputs were. I was like, turned on this one, boom. I wanted that output on. I want this output on. I want that output on, and I want this output on. Okay. So I got some 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, whatever. Okay. So what I could do is I could figure out which bits I want high, and then I could go right here and I could click decimal. 593. Okay, does everybody understand on a scale of 1 to 10 how I'm converting? I'm using this to convert between binary and decimal, and just make it a little cheat here on a tag called math tag, and it could be called math tag cheat if you want me to. Okay, you want to see this is something? There it is hex. Here it is ASCII. Hey, if you need to convert something to ASCII, if you need to convert it to octal, it'll do it for you. But if I just want it as decimal, I can do 593. Okay. So let's say I came to my program here, and let's say I was moving something, and I wanted to move it into the output module. Well, I could, let's say my destination, I don't know what I got going here. Let's see what my destination, let's say I had an output module here. Do I have an output module on this thing? I do. Local output 0. There you go. I just picked local 0 data, bang, okay? And then I could say, what do I want to move? I want to move 593, okay, to that right there. Is that right, 593? Let me look back here a minute. My number was main tag, monitor tags, 593. It was 593. So if I executed this move command right here, the decimal number 593 would get moved into my data right here, okay? And then what would happen? Well, at that point, according to this, I got to keep moving stuff around here, guys. That's why it's taking me a while. According to this, back to binary, outputs 0, 5, 7, and 9 would come on. Okay, and so this is just my way to kind of go back and forth. Or, you know, I could do math tag if you wanted to. If I went back to here, instead of doing 593, I guess I could have made that math tag. But really my math tag is just I use for calculations. So I probably wouldn't want to use my math tag there, because I change my math. I use my math tag a lot to do all this. Okay. Does this scale of 1 to 10 make sense here? How I could use the value of 593, or I could use the binary number, or I could use the tag name, or if you want to calculate this as binary, as hexadecimal, and then put hexadecimal into here, and I'll go for it, man. it'll still all work. So I see 10. Does this make sense? The way that I'm changing my numbers, and 593 is equivalent to the binary number, because you're going to be doing this a lot. Okay. All right. So I come back here. Oh, where'd I go? Right here. Okay. So I was kind of jumped ahead here. Where did we leave off here? We did this, we did this, we did this, we did that. Talked about binary addition, kind of showed you. You can change, this is on SIC 500, but you can change the radix right here, like I showed you, to octal, decimal, hex, okay? And then demonstration of the radix, I showed you that. And then the other thing that I did want to talk about was the system variable handout. And so we were having problems. Somebody was working ahead and we couldn't get the system variable handout to work yet. And I didn't have time to write the lab using a GSV. It's going to be a little more complicated. So it's your lucky day. We are not going to use the system bits, which I want you to read this, the system variable handout, because there'll be a question on it for the quiz. But versions 27 and higher doesn't really handle these system bits exactly the same way that the older ones do. So when you get to the lab right here, and it's talking about doing, SZ, SV, looking for my overflows and my underflows and all of this, and SC is getting my zero light and my overflow light and this, you don't need to put them in there, because it's not going to work on version 28, only works up to 27. So you can answer the questions here that are related to it. Okay, so same on the calculator. When you're here, you're not going to get those two to work. Okay, but you can still work with your calculator, and then you're going to take a look and you're going to see, what this looks like when you divide whole numbers here and getting decimals, because we haven't got to, we're still using integers. We haven't got to real numbers yet with decimal places. And so that is the goal of this, to take a look at this right here and see what's going on with decimal places. What's it doing? So on this lab right here, you want to take a look at part A. I would kind of maybe look at this and kind of in your mind, or even on a piece of paper, draw up what your different HMI screens are kind of going to look like, and think about what your PLC program is going to look like, so that you can get through this move and compare pretty fast. And here's where it breaks down. People that just show up and start trying to program this from scratch spend 4 hours doing part A, where it's about a 30-minute lab. All right, I'll say it one more time. If you spend 4 hours on A, I'm going to be livid, because you're like, what are we doing? No, we're moving compare. You should really look at this part A and try and get it done in a half an hour. So who's done with part A, and how long did it take you? I know I've got some people that are done with part A, and I just wonder, how long did it take you? Did it take you 4 hours? 30 minutes, I got somebody. Done, took about 45 minutes. 20 minutes for Ashton. Wonderful. I hate to compare people in this world, but there's going to be somebody in this class that takes 4 hours to do part A. And I'm gonna, you know how much of a nice guy I can be when you're not coming to lab prepared. You should come prepared to do this, and it will be done in 20 to 45 minutes. Don't take 4 hours. And then you can mess around with this number system and see what I was working like on this. I do want to remind you, unplug, where's that at? I'm going to put this right here. If I can add this on here. Unplug wheel, because it gets super hot, and there's like these little sticky things on the bottom that they just get really yucky. And then you get this sticky plastic on the table, and then it's there for like for the next 3 years. All right. So unplug wheel I've got. All right. So no system variables. Take a look at the lab. Hopefully it goes right. And then the other thing I want to just remind you on this, superior technology. I know, right? HMI deals directly with DINTs. Okay. The HMI is sweet. You put a dent in there, a dent's a dent, and then boom, you just multiply and add a dent or whatever. The thumb wheel needs the FRD. You got to BCD it in, and you have to then deal with it to get it to come out, right? You got to FRD, right? And then you got to TOD it, because it's a thumb wheel and it's dealing with binary coded decimal. The HMI, the beauty of it, just move it. You want to move it, add it, subtract it, compare it. It's just a tag name. Whatever the HMI brings in as a dent, if it brings in 375, bang, that's your tag. You don't have to do any of this stuff to it. So don't be trying to TOD an HMI value that you brought right in as a dent, because you bring 375 in, you get 375, and you are in business. All right. The TOD and the FRD is for the thumb wheel. All right, and we're just doing that to show you how it's going. Okay, I don't know what else to tell you. This is just the introduction to it. Hopefully we're flying through the HMI, creating your screens, runtimes, kicking it down, saving unique numbers. Oh, one more thing. Sorry, I'm talking a lot. It looks like we can do .mer version 12s, right? I was talking to Gavin. I forgot that we did update the HMIs to version 12. So you can create the MER file version 12 and kick it over, overwrite the communications, and hopefully your HMI downloads and connections and everything go really fast. And also, don't work 4 on a machine. If there are 4 people on HMI, it's going to take you forever. We got room to go 3, 3, 3, 2, 2 or something like that, or less. 3, 3, 3, 3, 2, 2, 2. I don't know. Like, spread it out, man. Let's get this done. 3 people are on 2 machines and 2 people on 3 or something like that. Okay. That's kind of what I got for you. You know, I expect you to read the homework, or the reading, and do the homework and understand the math. You got a quiz on the HMI tonight. That's not too bad, I don't think. But if you're reading and doing the math, this shouldn't be bad. And if you're reading of how to use these commands, it shouldn't be too bad. That's a short one. Another short one. I know. I'm sorry. What do you got? Talk to me. Otherwise, you can go take your quiz. All right, we're logging off. Good. Hopefully, it's the easiest quiz of the year too. Yeah.
Hey, Sean, I have a question.
Bring it.
When I was doing the calculator last week, it couldn't do fractions. Is that because we were using a dent, or maybe you shouldn't use a
Because
real?
it's not a real number. The real number would have a decimal point. So yeah, when you get a fraction, what's it doing? That's the goal. If you look at the lab, when you divide 36 by 72, I think is the one, right?
Yep.
What happens to it? It doesn't. 0.5 is not an integer, a whole number, right?
Yeah, I think you gave us a 0 or
0. Yeah, that'd be 0. Yeah.
yeah.
Okay. Yep. That's kind of what
Thank you.
we're taking a look at. And when you fill that calculator, be sure that those answers make sense to you, and then we'll review it again in the next lecture, right?
Yeah, I already turned my lab in, so you should have it by now.
Okay. Perfect. All right. Did my answer help you? Does that make sense?
Yeah. Thank you.
Okay. Yep. Okay. All right. Anything else? If not, you guys have a good weekend. Quiz should be open. Hopefully it's not too bad. I'll look, John, I'll look for your labs. I don't remember. I will stop recording.